We introduce SLS squared, a framework for probabilistically safe planning and control from pixels using latent world models, conformal prediction, and robust MPC. Latent world models enable planning directly from rich observations like pixels, which is useful when the true system state is hard to define or estimate. However, enforcing safety and task constraints becomes challenging. Learned latent dynamics are typically inaccurate without calibrated uncertainty bounds, and physical safety constraints need to be identified and enforced inside the learned latent space. Uncertainty and error in each can lead to failures. To address this, our method has three components. First, we learn a latent Markovian world model. Images are encoded into compact latent embeddings, and we construct the model state from both the current embedding and its recent changes over time. This makes the state more Markovian. It carries motion information, not just appearance, so the next latent state can be predicted from the current state in action. An action condition dynamics model then predicts future latent states for gradient-based planning. Second, we learn a latent obstacle classifier. Safe and unsafe observations are labeled from task constraints encoded into latent space and used to train a classifier. We use conformal prediction to calibrate the classifier threshold and provide conformalized constraints, giving us a conservative latent safe set for planning. Third, we use system-level synthesis for robust MPC. SLS jointly optimizes the nominal trajectory, controls, and closed-loop responses. These responses define reachable tubes under calibrated model uncertainty, and constraints are tightened so the tubes remain safe. Together, SLS squared plans in a learned Markovian latent world model while using conformal calibration and robust feedback synthesis to enforce safety. We evaluate two versions of our approach: nominal gradient-based MPC and robust MPC. In the nominal case, the key contribution is our Markovian latent world model, which creates an optimization-friendly latent dynamics model for long-horizon ILQR planning. In the robust case, we extend this planner with learned latent safety constraints, conformal calibration, SLS reachable tubes, and constraint tightening, so constraints remain enforceable under imperfect latent dynamics. Below, we provide timestamps for each result in this video. First, we look at nominal planning across Reacher, Cube, Push-T, and Rope. On Reacher and Cube, our Markovian latent world model with gradient-based planning shows stable convergence to the goal. For Cube, the baselines can sometimes move close to the target, but often drop the cube, while our method reliably keeps it in hand. Push-T is the hardest nominal task because it requires complex, long-horizon contact maneuvers to align the T-block with the target pose. Our MPPI plus tracking ILQR planner achieves 51.54% success, while the other methods stay below 5%. For bimanual rope manipulation, our method quickly converges to the desired rope configuration with much lower goal-reaching error than the other planning methods. We also replicate this task on hardware, where the robot stably reaches the target rope pose from pixels alone without using ground truth state measurements of the rope. Now we move to the safety results. Across Reacher, Cube, and Rope, the nominal planner often reaches the goal by using unsafe behavior, entering the unsafe region in Reacher, lifting the cube too high in OG bench cube, or taking the rope through the obstacle in Rope. With SLS squared, we impose these constraints directly into the learned latent space. The planner changes its behavior to avoid unsafe regions while preserving stable goal reaching. Across these robust tasks, the reachable tubes remain tight and execution tends to stay inside the probabilistically valid tubes across successive planning steps. Overall, the results show two things. Our latent world model improves long horizon goal reaching from pixels, and SLS squared adds robust safety without destroying the planner's ability to complete the task. To conclude, we summarize our method with the following bullet points and our block diagram. Thank you for watching.